So in this video we are going to see the most important three derivations which is 100% going to appear in your board exam. Before going with how we are going to derive this derivation, first we have to understand that what we are going to derive. So basically in all the three derivations we are going to derive a term called as that of your packing efficiency. In simple words, if I have to say what do you mean by this packing efficiency means, for example, if you are having a plastic cover, okay, what is the maximum number of the content you can put in that plastic cover? That maximum content is called as that of your packing efficiency. Similarly, in these derivations, we are going to select a particular unit cell. It may be your body centered, it may be your face centered, and it may be your simple cubic. And we are going to state, or we are going to derive that what will be the maximum number of the atoms that could present in those unit cells. Or in simple words, what is the percentage of the total space will be covered by these atoms in the particular unit cell. I am repeating once again. In these solids, the packing efficiency refers to the percentage of the total space covered by the particles. So let us now first begin with to derive the packing efficiency in a crystal of that of your body centered cubic. Just recall how does your body centered cubic lattice will be. Of course, in a general way, if I draw it, we know that in body centered cubic lattice the particles will be at the corners and also in body center. So in this part we are just going to take any one part. I am just selecting only one part so that my derivations would be easy. Okay, so first you want the foremost thing, you just draw your unit cell. Okay, we have drawn our unit cell. Now I'm just taking one sphere at one corner. Please note it down, I'm writing it. Yeah. Another sphere is over here. See, it is touching the sphere which is adjacent to it. And one more sphere over here. Like this. All the three spheres are in contact with each other. So now let us assume, since it is a cube, we know that all the sides should be equal. So let this be edges length. All the edge length will be A itself, no matter with that. Okay. So let me give a naming. This be A, B, C, D, E, F, G, and H. Let me draw a diagonal from here. Okay. Let this diagonal be your C. Okay. This diagonal be your C. Okay. I'm just drawing one more line over here. Let this be also a diagonal which is called as that of your FD. Let me call it by a term of your B. Let BFD be a diagonal. Okay, so what we have considered, let the cubical edge length be E, let the diagonal FD be a diagonal which is having represented by a unit of B. Okay, so now from this cube we are having the two triangles, if you can just observe. One is E, F and D, and another I am choosing a triangle of that of your A, F and D. Able to understand? First I am choosing a triangle of E, F and D, and another I am going to choose a triangle of A, F and D. So from the triangle, when you are choosing of E, F, D, when you are choosing a triangle of E, F, D by applying your Pythagoras theorem, what you can say, let me choose my FD square. What is that? Your FD square is equals to that of your EF square plus ED square. EF square plus ED square. So FD square is equals to ED square plus that of your Where is that one? Yeah, FD square is equals to EF square plus that of your ED square. Of course, this length is also that of your A itself, or edge length. Since it's a cube, it's a symmetry. So what you can write over here, B square is equals to A square plus A square. So B square is equals to 2A square. Okay. This was with respect to the triangle of that of your EFD. Considering the triangle now AF and D. Considering the triangle AF and D. Here also what happens here, AF square, of course what you require, the diagonals, that one only I am choosing over here. AF square is equals to FD square, yes, plus AD square, plus AD square. Of course this length is also equals to A itself. So next what you are going to say, AF square is how much? It is equals to C square. That is equals to FD square is how much? B square plus AD square is A square. You better understand. We know what from the part B square is equals to 2A square. So let me just substitute over here. If I consider here this one as 1, let me substitute B square value of 1 in 2. Okay. So what you will be getting, C square is equals to 2A square plus A square, or C square is equals to 3A square. If I am taking my just C, so what happens over here, of course the square root belongs to both, but this will be equals to root 3. Square root of A square means square and the square root gets cancelled, so you will be getting as root 3A. So C is equals to root 3A you are going to get. Is that clear? Now the question arises, what is this C? If you can closely observe over here, if I am taking, say, let this be in like this. 3 spheres which are in of equal size are in contact with each other. Alva. So of course in my diagram you could just see that from center like this to over like this to another center it has been gone in this figure. So I have called this one as my C. We know that whenever you're choosing a circle, half of this from the center, the distance is called as that of your radius. So what can write? So this will be 1 radius R. Of course they are all equal size spheres, so R all are equal. So this is also R, this is also R, this is also R. So R plus R plus R plus R. So C will be equals to what? 4R. So can I write over here now? So 4 times of the radius will be equals to root 3A. So from this, let me check out what will be the axis length of the cube. So 4 by root 3 into A. Sorry, a mistake. 4 by root 3 into R. Alva. So A means what? They are the edges length, whatever we have done over here for a cube, and that we are getting for a body centered cube as 4 by root 3 into R. Now the question arises, we know what volume of the cube, or the volume of cube means what? This is a unit cell. Volume of a unit cell will be equals to the volume of the cube itself. Alva, since it is a cube. What is the mathematical expression for a volume of a cube? It is A cube. So from this third equation we can write as how? 4 by root 3 times of R the whole cube will be giving you as the volume of a cube, or it will also called as a volume of a unit cell. This is our one unit cell, body centered unit cell. Yes. Now we have to check out in BCC what is the number of the atoms present. From the 8 corners it contributes to the 8 other unit cells, and we know it is 1. For the body center it is none other than shared with that respective unit cell, so it will be only belong to the body center unit cell itself. So total number of the atoms in a body center cubic unit cell is 2. Is that clear? Then what will be the volume of the sphere over here? Volume of sphere. Why volume of sphere? Because here whatever the atoms we have chosen, we have considered them as a hard sphere. From the mathematical expression, what you know, volume of a sphere is 4 by 3 pi r cube. Is that clear? So from the body center we came to know that there are total number of 2 atoms and each sphere is having a volume of 4 by 3 pi r cube. Now let us go to the major definition of packing efficiency. So what do you mean by packing efficiency then? What is the formula? It is given as number of the atoms in a unit cell, yes, into volume of the sphere divided by total volume of unit cell into 100. Let me write it down. Packing efficiency is equals to number of the atoms in unit cell, in a given unit cell, okay, into volume of the sphere divided by total volume of unit cell. Total volume of unit cell. So keeping this one as our definition or the formula, we know what in a body centered cubic unit lattice the number of the atoms in a unit cell is, of course it is 2, and each is having a volume of the sphere as 4 by 3 pi r cube. It is actually a mathematical expression, volume of a sphere whole divided by total volume of a unit cell. I have mentioned earlier itself, it is like a cube. So total volume of a unit cell will be volume of a cube, which is equals to a cube, and we have derived what is the value of a. So from that part I am going to write as 4 by root 3 r the whole cube. Alva. So when you are going to solve it, we are going in a percentage. Since packing efficiency means it's a percentage of the total space covered by these atoms. So when you are solving it, percentage means into 100. This one also into 100 since it is a percentage one. So when you are solving this, we are getting the value of 68%. So what is this 68% refers? So in a body-centered cubic unit lattice, when you are considering all the atoms, of course from the 8 corners and also at the center, we will be able to see that these atoms will be occupying only 68% of that of the total unit cell content. The space covered by all the atoms at the corners and also at the body centered will be equal to that of your 68%. That is the reason we are saying that packing efficiency is the total space covered by all the particles in a system. If you are considering this one as a body centered, if you are considering all the atoms in the corners and also at the center, only 68% of the space will be covered. So this is with respect to that of your body centered cubic unit lattice. Very much important. Here the value of A and that of the value of your packing efficiency. So in my next video we are going to see another derivation with respect to that of your hexagonal close packing, or it's also called as cubic close packing. Please remember this cubic close packing is none other than that of your face centered cubic. We have mentioned its another name. So that will be with respect to the face centered unit cell. Okay.